All right, so let's start talking about functions. If you ask me what pre-calculus is really about, I would answer that this course is a year-long exploration into functions, understanding their domain and their range, understanding how they operate, how to evaluate, um, graphically some of the conditions and characteristics of functions, and we explore a various number of types of functions throughout this course. So it's really important for us to get on just a really good start and understand some important terminology and notation for functions. So before we talk about functions, understand that a set is simply a collection of values. So a function is a type of relation in which inputs and outputs, or one set of values, is related to a second or another set of values. So it's a relation between two different sets of values. And a set of values, again, is just a collection of values. And whenever one collection gets connected or related to another, we have what could be a function. Now I say could be because there's a specific condition for something to be a function and not just any other relation. We'll get to that in a second. Understand that the notation for functions is often read as f of x. You see me underlining it here, f of x, or f evaluated at x. And what you're seeing here is the function itself. It's what the function is doing. Oftentimes when I describe functions, I kind of will illustrate for the student this idea that there is a machine. The function is like a machine, it's doing something. So we're plugging something into the machine. Our function has some kind of rule, and then something is coming out of that machine. So in this case, for example, we would say that this function is we're going to say f of x is equal to x squared. It is going to square whatever input you plug in. And this input here, anything that you can plug into the function, is what's also known as our domain. It refers to the values that we can input into our function. Whatever comes out of it, this would be our output. And all the values that are part of the set of output values, we would call our range. It's a set of elements that are part of the output. Now, I said earlier that not every relation is a function. What makes something a function specifically? Well, the key idea behind a function is that every input, and I'll write this at the bottom here, every input has exactly one output. And let me try to illustrate that with what I am showing you here. I've got two different relations. I've got x and f of x, and although I say f of x here, the idea here is that we have got an input and we got an output. What we're going to see is these two relations. Which of these are functions, if any? So look at the first one. We see that 1 results in 2. An input of 2 results in 4. An input of 3 results in 6. And an input of 4 also gives you 6. Well, in this case, is this a function? Pause the video and think about that. And the answer is yes, this actually is a function. Even though 6 appears twice as an output, both 3 and 4 give you 6, and that is fine because 3 has exactly one output, which is 6, and 4 has exactly one output, which is also 6. Now compare that to what's going on in this second relation here. So let's take a look at this one here. Pause and ask yourself, is this relation a function? And the answer here is no, this is not a function. Although 1 does result in 2 and has just one output, notice what's happening here with 2. 2 results in 4, and then when you try 2 again, it results in 6. So this is not a function because 2 has two different outputs. Therefore, we would say this is not a function. So now that we have seen a couple of examples, I'll do a few more. Looking at this one right over here, I've got x and f of x. Let's look at some of these examples here. I've got 1 resulting in 3, 2 resulting in 5, 3 also results in 5, and let's continue this here, 4 results in 6. Ask yourself, is this a function? And the answer is yes, this is a function because we're seeing here that 1 gets mapped to 3, 2 gets mapped to 5, 3 gets mapped to 5, and although these outputs are the same, 2 has just one output, which is 5, 3 has just one output, which is also 5, but that's fine because it has just one output, and 4 has one output, which is 6. Now for number 2, it might be hard to see this unless we see a graph. And if I were to graph this right now, and this is a pretty easy one to graph, it's just a parabola with a vertical shift down 1. So I'm going to just do a rough sketch here. And looking at this, we can ask ourselves, does it look like every input has exactly one output? And the answer is yes. Therefore, this would be a function. And one way we could tell if that is the case graphically is something called the vertical line test. The vertical line test. And the idea behind the vertical line test is if you can draw a vertical line anywhere on the graph and it intersects or crosses the graph just at one unique spot, then it passes the vertical line test. It is a way of informing us that every input has just one output. If it were to cross twice, you'd be seeing it going through two different outputs for a specific one input. So for example, let me just draw an example of something that would not be a vertical line test, that would not pass a vertical line test. If we had some graph that looked like this, and now I try to draw a vertical line, suppose I drew a vertical line here at, let's say this x value were 4, I would see that 4 has two distinct outputs. It does not pass the vertical line test, which tells us that we've got one input with multiple outputs. Therefore, this would not be a function. Now look at number 3. Is this one a function? And the answer is no. This is a set. In fact, this is not even a relation. So there is no function because there's not even a relation here. It's just a collection of values. So now let's practice evaluating some functions here. So to evaluate a function does not mean to solve. It means to find the value of the function at a given input. So we've got a couple of different inputs. I'll run through these pretty quickly. If I want to find the value of the function at the input of 2, so again, if we go back to that machine example here, right now what I'm plugging in, I'm plugging the value of 2 into this function, and I'm seeing what comes out. That's what I'm doing when I'm evaluating a function. So with that in mind, if I plug 2 into this function here, let's just kind of go back to this. If I plug 2 into this function here, we're going to say 2, and in place of the x, I'm going to substitute a 2 squared minus 3. So this 2 times 4 minus 3, and I can say f of 2 is equal to 5. Let's try f of 5 now. Go ahead and pause the video and try that one on your own. Well, hopefully you found that this was 2 times 5 squared minus 3. So 2 times 25, which is 50, minus 3 is 47. Now let's try an example where we're going to plug in an algebraic expression that's not just consisting of numbers. So f of x plus 2. Our function was 2x squared minus 3, so we're going to go 2 times our input squared minus 3. And in this case, our input, let me actually even kind of highlight this. We'll make this green. Our input here is x plus 2. That's what we're plugging in to our function. So this is going to be 2 times x squared plus 4x plus 4 minus 3. We're going to combine like terms. 2x squared plus 8x. 2 times 4 gives you 8 minus 3, which is plus 5. Okay? And I'm going to let you try 3x on your own. Now let's quickly talk about piecewise functions as well. A piecewise function is simply a function that is split up into a number of pieces or parts, if you will. And essentially it's saying depending on what your domain is, you are going to do a different function. So in this case here, this piecewise function is saying if your x value is less than 0, then the rule of the function is saying you're going to multiply your input by 3. On the other hand, if your input or your domain is greater than or equal to 0, then you are going to square your input. So let's try a couple of these. So if our input is negative 3, we're finding f of negative 3. Ask yourself, which piece would I plug this in? Well, negative 3 is less than 0. Therefore, we're going to use this top function. So I'm going to switch to red here, and I'm going to say 3 times negative 3, which is equal to negative 9. Okay? Now let's try the next one. What about f of 0? Ask yourself, which piece would I plug this into? Well, this is f of 0, which means I'm going to plug it into the second piece since my domain here is greater than or equal to 0. 0 is equal to 0, so I'm just going to say that this would be equal to 0. And finally, try f of 4, and hopefully you're getting this by now. We know that when we plug in 4, we're going to plug it into this particular piece, so 4 squared is equal to 16. Okay? So I'm going to let you try to do some of those classwork problems on your own. And I want to just jump to real quick, maybe just doing one of the more complicated ones. Sorry, there's a brace there that doesn't need to be there. Let's try number 3 together. Let's evaluate this function now, given these domains. So pause the video and give these a go. So if we evaluate h of 6, we're going to say the square root of 6 minus 5, which is the square root of 1, and that's just 1. H of 14, which is the square root of 14 minus 5, which is the square root of 9, and that's equal to just 3. H of x squared plus 5, now we're plugging in x squared plus 5, that's going to give me x squared plus 5, and then we're subtracting 5 in that radicand, and then we get the square root of x squared. So we can either write this as the absolute value of x, or plus or minus x. Either one of those will work. Okay? All right. Finally, oh, actually, I don't want to say finally. There's 2 more quick things. One, let's talk about finding the domain of a function. The domain of a function is simply the set of all values for which the function is defined. We've already talked about domain quite a bit in this lesson and as well as previously in our Appendix B. The key idea here is when we're finding domain, we want to find all the values for which this function works and can operate and can give you a valid output. And oftentimes, it's much more efficient to come up with which values don't work. Think of it as like a party. It's often faster to say everyone is invited except for Steve. Sorry, Steve. But it's much faster to say that than to list every single person who is invited. So it's often more efficient to come up with what we call domain restrictions, the values that cause the function to be undefined. So, for example, the 2 primary types that we need to worry about right now is when we have quotients or rational functions and you see a variable in the denominator, we know we can't divide by 0. So our domain restriction, we would say, would be x is equal to 0. That is the one value that causes this function to be undefined. And we would describe our domain as being all the numbers from negative infinity to 0, union 0 to positive infinity. Now, what about something like an even index radical? Well, we know that we cannot take the square root or an even root of a negative radicand. So we know that x minus 1 must be greater than or equal to 0, which we then say x then has to be greater than or equal to 1. And in interval notation, we would say that our domain is therefore all the numbers from 1 to infinity. Let's try another problem like that. So let's try this one here, where I'm asking you to find the square root of 1 minus 2x, the domain of this function, excuse me. Well, again, it's very similar. We know that this must be greater than or equal to 0. So we'd say 1 minus 2x is greater than or equal to 0. Negative 2x is greater than or equal to negative 1. Flip that inequality symbol since we're dividing by a negative, and we can say x must be less than or equal to 1/2. Therefore, the domain here, we would say, is from negative infinity to 1/2 inclusive. Let me jump to something like number 3. What about for something like number 3 here? If I ask you to find the domain of this function, well, again, we know that 2x minus 1 must be greater than or equal to 0. However, pay attention to this function here. You'll notice, by the way, I am missing a function notation here. You'll notice that our radical is in the denominator. So not only does 2x minus 1 have to be greater than or equal to 0, it's actually more specific. It can only be greater than 0. And ask yourself why. Again, because this is in a denominator, we know that we can't plug in anything that will ever cause that denominator to be equal to 0. So we would say it can't include anything 0. So we would say 2x must be greater than 1, x is greater than 1/2. Therefore, my domain would be from 1/2 to positive infinity. Okay. Well, hope this video has helped you understand a basic understanding of functions. In the next video, I'll briefly talk about the difference quotient.